All right, welcome to The Explainer. Today we're going to pull back the curtain on software engineering. And here's the thing, it's a discipline that was born not just because of computers, but because of the limits of our own minds.
Okay, so check this out. This graph, it basically shows two possible futures for any software project. You've got that green path, right? That's the dream. That's where your effort and costs grow nice and steady. But then there's that red path, and that, my friends, is the nightmare. It's what happens when things spiral out of control. Your costs, your time, your effort, they don't just grow, they explode. It's an exponential mess.
So, what's the difference? Why does one way of doing things lead to total chaos, while the other leads to control? Well, the answer, and this might surprise you, isn't really about the code. It's about the fundamental wiring of our own brains. Seriously. So before we can talk about the solution, we've got to really dig into the problem. Let's take a look at the way people used to build software, the approach that software engineering was invented to fix. So you might have even done this yourself. It's what we call the build and fix approach. You know, you get an idea, you start writing code, you run it, oops, there's a bug, you fix it, you just keep repeating that loop. And look, for a tiny little program, maybe 100 lines of code, it feels great. It feels fast. But here's the trap. Try to build a 10,000-line system that way, and you end up with this tangled, unmaintainable nightmare where the costs just go through the roof.
So why? Why does that totally intuitive approach fail so spectacularly? Well, it all comes down to a hardwired limitation baked right into our brains.
Okay, think about your brain for a second. It's kind of got two different memory systems, right? You've got your long-term memory, which is like this massive, enormous library holding pretty much everything you know. But the memory you're using right now to think, what we call short-term or working memory, that's more like a tiny little sticky note. It's super fast, but man, it cannot hold a lot of information at once. So just how limited are we talking? Well, it pretty much boils down to this number. 7, give or take 2. And this isn't just some random guess. It seems to be a fundamental constant for how we think.
Yeah, way back in 1956, a psychologist named George Miller wrote this super famous paper about what he called the magical number 7. And what he found was that our short-term memory can really only juggle about 7 different things at one time. Once you try to hold more than that in your head, our ability to think clearly about a problem just tanks.
Now, our brains are pretty smart, and they have this built-in trick to deal with this limit. It's called chunking. Basically, we group related bits of info into a single chunk, so it only takes up one of those 7 precious slots in our brain. Like, trying to remember that long string of ones and zeros is, well, it's pretty much impossible, right? But if you group them, if you chunk them, they suddenly become a number you can actually remember, 6251. It's manageable. The huge problem for software developers is when a program gets so complicated that you can't chunk it anymore, you're lost. And this is where software engineering saves the day. It's not just a bunch of boring rules. It's a collection of really powerful techniques designed specifically to help our brains handle this insane complexity, to work around that cognitive limit. And you'll find that pretty much every single technique comes down to 2 core principles: abstraction and decomposition. You can think of them as our 2 primary weapons in the fight against cognitive overload. So, first up is abstraction. This is basically the art of ignoring stuff that doesn't matter right now. The perfect example is a subway map. I mean, think about it. It's an incredibly useful model of a city, but it's useful precisely because it leaves out almost everything. It hides all the individual streets, the buildings, the trees, all that overwhelming detail. It just gives you exactly what you need to solve one problem: how to get from point A to point B. And once you see it, you realize we use this trick everywhere to manage complexity. An architect's floor plan, that's an abstraction. It ignores all the plumbing and wiring to just focus on the layout. Even biological classification, kingdom, phylum, class, that's just a way to take trillions of individual organisms and group them into a hierarchy that we can actually understand. Okay, then you have decomposition. This is the classic divide and conquer move. Instead of trying to wrap your head around one gigantic, complex system with like 100 moving parts, which is totally impossible for our little 7-item memory, you just break it down, you chop it up. You end up solving, say, 10 smaller, simpler problems, and each one of those is small enough to actually fit inside your head. Okay, so we have these 2 amazing principles, but how do we actually use them? Well, they're put into practice through structured methodologies. Think of them as blueprints for building software.
The whole thing starts with getting that blueprint right. In the software world, we call this the Software Requirement Specification, or SRS. You can think of it like a legal contract that defines in excruciating detail every single thing the software has to do. And I'm not kidding when I say getting this part right is absolutely 100% critical. And this chart right here shows you exactly why. Let's say you catch a mistake in the requirements phase, the very beginning. Maybe that costs you, I don't know, $1 to fix. But if you don't find that exact same mistake until the product is already out in the wild being used by customers, that fix could cost you thousands of dollars. It's not a linear increase, it's exponential. The later you find a bug, the more it's going to cost you. Period.
So the early ways of building software, like this thing called the waterfall model, were super rigid, very linear. You had to completely finish one phase, like requirements, before you could even think about starting the next one, design. It just flows downwards, like a real waterfall. It's very structured, which is nice, but it has a huge flaw. It leaves zero room to change your mind once the project has started.
So in complete contrast to that, you have modern approaches like Agile. These are built from the ground up to be flexible. They work in these short, repeatable cycles called sprints, usually just a couple of weeks long. And at the end of every single sprint, the team delivers a small but working piece of the software. They get feedback on it, and then they use that feedback to adapt their plan for the very next cycle. It's all about iteration and adaptation. And to make sure they're on track, teams use simple visual tools like this sprint burndown chart. It's nothing fancy, just a graph that shows how much work is left to do over time. That downward sloping line is what you want to see. It gives the whole team this instant, transparent feedback on whether they're going to hit their goal or not. No surprises.
So at the end of the day, all these principles, all these methods, the goal isn't just to get the project done. It's about building software that is high quality, that's reliable, and that someone can actually maintain and update for years to come.
And when we talk about good design, two words you'll always hear are high cohesion and low coupling. Okay, what does that mean? High cohesion means that each piece of your software, each module, is laser focused on doing just one thing and doing it really well. Low coupling means that all those different modules are as independent from each other as possible. You want them to be like polite neighbors who just wave, not roommates who share everything. That way, a change in one doesn't break 10 others. And when it comes to testing, actually finding the bugs, engineers have to deal with this really fascinating problem. It's called the pesticide paradox. Think about it. If you spray the same pesticide on a field over and over, eventually the bugs that survive are the ones resistant to it, right? Well, software tests are the same. If you keep running the exact same set of tests, they become really good at finding those specific bugs, but they become totally ineffective at finding any new ones. The remaining bugs are, by definition, the ones your tests can't catch. So you always have to be changing and diversifying your testing strategy. So this brings us to the big final question. If software is just built on pure, cold logic, why are the biggest challenges always human? And that's really the crucial takeaway from all of this. Software engineering isn't really about talking to computers. It's a deeply human discipline. It's a whole toolkit of principles, processes, and mental models that we invented to help us overcome our own built-in cognitive limits. It's what allows us to work together to build these incredibly complex systems that no single person could ever create alone.